Now, part of the reason we talk about moment couples is to get to vector transfer. So that's the next step towards rigid body equilibrium. So what is vector transfer? Well, let's say we have a line of action AB with force F acting from A, and we want force F to act at B instead. Well, what we do is we can come over here and add force F over here at B, and a negative force F here at B. So if I have a positive force F and a negative force F at B, what do I have? 0, which is what I started with. However, I could also look at this as a positive force F at A and a negative force F at B. Those two also cancel each other out, so I'm left with my transferred vector at B. What if my force F is not acting along the line of action AB? Now what? Okay, well, I do the same thing. I can move it over here to B by adding a negative and a positive. Okay, but this time, when I add my positive F at A to my negative F at B, they do not subtract out entirely. The magnitudes subtract out, but what we have created is equal magnitudes, opposite senses, and parallel lines of action, meaning they are now a moment couple. So what we have learned here is I can find a resultant force and a moment couple to transfer a force from one location to another. And this is the concept that I'm going to be using for rigid body equilibrium a couple lectures from now. For example, if I have a system with a 100-pound force acting at B and 265-pound force acting at C, and I want to find the equivalent force couple systems acting at A and C. The objective here is to get our two forces at two different locations down to one force and one moment couple at one location. My force acting at C can be broken apart into a horizontal component of 240 pounds and 100 pounds. And I found that using similar triangles. So I have 100 pounds acting in the I direction for force B, and I'm going to add that to 240I plus 100J acting at point C. So my equivalent resultant force is 340I plus 100J, and we will be in pounds. Next, I need to sum my moments about A. So that is going to equal to the moment at B, 100 pounds, acting at a distance of 2.5 feet. And that causes a clockwise moment about A, so that's negative. And then I have the 100 pounds acting at 4 feet. That's the vertical component at C, and it is acting counterclockwise. And then I have the 240 pounds acting vertically at 0 from A. So that is going to be unnecessary in our equation. My moment at A is 150 pound-feet. Acting counterclockwise. Moments at C. Once again, I'm going to have the moment at B, 100 pounds. It is acting vertically 2.5 feet from C and is causing a clockwise rotation. Then I have the 100 pound and the 240 pound forces that are both acting at C, which means there's no distance at all. So my equivalent moment couple at C is 250 pound-feet. Clockwise. Okay, to represent this visually, to move everything to point A, we would have our resultant force here acting at 340I plus 100J pounds and a counterclockwise moment couple of 150 pound-feet. For C, we would have the exact same resultant force, but we would have a clockwise 250 pound-foot moment.